Namely, the story goes that Professor Futamura was giving a lecture, and the light bulb burned out on his projector. So then they brought out another projector. This one worked for a little while, and then it failed, so they brought out the third projector, and finally at that point they had the third Futamura projection, and everything worked. So that seems to be what's happened here. And somehow, no matter how deep the theoretical and programming fact, you can always have a little bit of a hardware problem, and then that's life. Okay, what I'm talking about is having to do with programming languages. I learned how to program in 1960, and I found programs were fascinating objects, and that fascination has stayed ever since then. That's taken many different forms. It's partly led to a couple of books, and what I'm going to describe today is a couple of the high points of this, and it's fairly elementary. I'm not going to be assuming a lot of previous knowledge. But basically, what is a programming language? Just thinking of it from the outside. A programming language, here we called it L, just to have a name, consists of basically two sets. There has to be a set of programs and a set of data. Now, the place that makes programming languages interesting is that programs can be data. And that was one of the first things that I discovered in the early days, was that a compiler was a data object. It was a text file. And a compiler could compile itself. It was possible to bootstrap compiling. And this led to a number of different things. I spent 4 years writing a compiler for Algol 60, and we used a lot of bootstrapping in the process. Furthermore, the programs are not just data. They have to have an interpretation. There has to be a way to execute the program. And I found a useful way of saying this is to say that there is a function which for each program, P for program, the semantic function of that program is what it does. And for this talk, it's enough just to talk about input-output functions, that the program is given some inputs and produces an output. It may also fail to terminate, which is why the arrow is not a complete arrow. A programming language is usually equipped with some things of practical interest. For example, you can measure the number of steps that running a program takes. Or you can measure how much memory space, how much storage is used to run the program. And of course, these are very important. You can't abstract away from time and space. Now, people studied computability long before computers existed. Back in the 1930s, people were doing the theory of recursive functions, which is essentially the basis of what computers do nowadays. For computability theory, the main requirement, whoops, let me get this back again. Yes, was that a language should be Turing complete. A function is computable if and only if it's computed by some program. And this looks a little circular, but it can be defined sharply. There should be two other conditions. There should be a universal function property. There exists an interpreter, a program that can run any other program, or even run itself. So the effect is that the result of running a program on some data can be obtained by running the interpreter on that program as data. So you give the interpreter two inputs. You give it the program it's executing and the data that program works on. This is a very familiar concept in computer science. It's a self-interpreter. It's something that you've probably seen many of at the at the hardware level, there are a lot of self-interpreters that are being used. At the higher level, in, say, Scheme or Lisp, is easy enough to write a self-interpreter. And the other property is one called specialization, and saying that if you have suppose you have a program that has two inputs, I'll call one the static input and the other a dynamic. What a specializer does is it takes the program and the static input and it produces a new program, such that if you run it on the rest of the input, you get the same answer as you would have run P on all of the data. And this is you have to look at it and think a little bit about it, but it's basically fairly straightforward. I'll show you a picture or two that may make it clear. But basically, the idea is that P specialized S is the program P with the static data built into it. And a trivial specializer would work this way. A non-trivial specializer would use the static data. It would do as much of P's computations as it can that depend only on the static data and generate code for the rest. So this is pre-computing, and the output of that is the residual code. And this term, the residual code, in fact, is something that Turchin and Yashov used many years ago. Now, interpreting and compiling. I've said what an interpreter was. It's a program which can achieve the effect of any program, including itself. The interpreter works at one time phase. It is running the program sort of online. A compiler works in two phases. A compiler takes a program and produces a new program, a target program, and then in the second phase, that target program is run on the data. So a compiler could transform from one language into another, and often they're used for that. But it makes sense even to talk about compiling on a single language. And finally, a specializer, you can describe that by similar equations. The result of running P on two inputs is the same as a result of specializing P to the static input, giving a new program, which you then run again, then run on the dynamic input. Now, this specialization is the trickiest part. Normally, when you run a program, it has, say, in this case, two inputs and produces one output. With specialization, you take the program and the static part of the input and produce a new program. Then, at stage two, you run that input to get the final output. So it's what's often has been called a staging transformation, given it divides the computation of P into two stages. Now, why would you want to do this? It's not entirely clear. But what you can refer to something that we call the speed up, which is the time to run the original program on the data, divided by the time to run the specialized program on the same dynamic data. Now, usually, the specialized program will run faster because you can pre-compute based on the static input. So usually and that's why we call it speed up. It could be a slowdown. You could imagine a specializer that made programs run slower, but speed up is normally what you want, and you can achieve speed up. What about interpretation? Well, an interpreter is something that doesn't execute P immediately. Rather, it looks at the program and says, what is the next instruction? Then, once it knows what that instruction is, then it performs it. And then it goes to the interpretation loop goes to the next instruction again. So it's continually finding out what to do and then doing it. So that's slower. That is not as fast as running the program on hardware, say. And interpretation normally gives a slowdown. It gives flexibility because you can interpret many languages, but it's often, say, 10 times slower. Now, a specializer, you could specialize that interpreter to a given program. And if you can remove that overhead, then you've got a good specializer. This is one of the, been achieved in practice. In the mid-'80s was when it was developed. A key point in it, it was done partly by our group in Copenhagen, but a key point was to achieve optimality, to achieve this fast, efficient specialization, was the idea of arity raising, which was an idea that Sergei Romanenko came up with. And his group has worked on that for a number of years. And it's called arity raising. I won't go into the details of it, but it's just one sign that this development, this research line, has had a fair amount of interaction with Russian researchers and Western researchers through the years. And that makes it interesting. Now, finally, we're getting to the Futomura projections. And no, it's not a slide projector. It is a program transformation. What we'll show is that a partial evaluator can be used to compile. It can be used to transform an interpreter into a compiler. And it can even be used to generate a compiler generator. Now, this was discovered, as far as I know, for the first time by Yoshihiko Futomura in 1971. He published a paper with some of the ideas in it, and the idea has been rediscovered since then. I know that Valentin Turchin rediscovered it in the context of supercompilation. I've heard just today that Yashov had apparently realized the same thing in the mid-'70s. What are these projections? Well, they're saying that you can build a target program by specializing the interpreter to a source program. That's the first one. The second one is that you can build a compiler by specializing the specializer itself to an interpreter. And finally, the third one is even harder to understand. The specializer is being specialized to itself with respect to itself as its first input. That's the main theme of this talk, is this fascination with the idea of programs that are run on themselves, programs that are self-applied. The Futomura projections, the second and the third, both involve self-application. And that's the general theme. And I think I can walk through the reasoning of how this works. Now, recall that an interpreter, it runs a program on an input, and it produces an output. But the way it does it is it is given the source program and its input. Now, suppose we want to execute the same source program on several different inputs. So we want to compute an output 1 for input 1 and output 2 for input 2, and so on. The idea of the first Futomura projection is say, well, in each of these cases, the first input is always the same. It's always the source program. So let's specialize the interpreter with respect to that source program. So we'll call that the target program. Now, what does it mean to be a target program? Well, a target program should do the same thing as the source program does. It should compute the same answers. Hopefully it may do it faster or slower, but it should be correct. It should do the same. And we can see, in fact, that it works because the target program, if run on an input, would, by the definition of a specializer, be the same as running the specializer on the input and the source to give a new program, which is then run on the input. But this is what we just call target. So in any case, that these two are equivalent is because of what a correct specializer is. And this one, interpreter of source and input, that is what we call the target. So that's the net result of running the target program. So what do we have? We have that this target program is on the input is giving the same output as the source program would have given to begin with. And so this means that it is a correct target program. It's so what we're doing is we're going from a very general purpose program, the interpreter, to a very special purpose program, namely saying, I want to interpret this one source program. And the specializer is achieving that effect. We can express it more symbolically by the algebraic. Remember what a specializer is it's a program that for any P with static input and dynamic D can achieve its effect in two stages. So if we claim that the target program equals the source program, we can show that. The output is the result of running the source on the input. That, by the definition of an interpreter, is the same as the answer from running the interpreter on the source program of the input. Now, if we take this equation up here and just let P be the interpreter, S be the source, and D be the input, then that's just an instance. This equation is just an instance of this. And what you've got this, well, remember we said that target was the interpreter, was the result of specializing the source program interpreter, and this gets the output. So the net effect is that the target program computes what it should, the function that the source program computed. So assuming the specializer is correct, which is this always yields a correct target program that is correct. So what's happening here is that the interpreter is, the specializer is a bit like half compiler and half interpreter. It's taking a program, it's executing the actions it can that depend only on S, and it's generating code for the operations it doesn't have enough information to do. So it's both executing and generating code. We can also generate a compiler from an interpreter. And why is this interesting? Well, interpreters are smaller. If you've ever written an interpreter, you know it's a lot easier than writing a compiler. They have the logic is simpler. They have only one time. You don't have two stages. You don't have to think about what do you do now to be sure that something will happen at runtime. And they're easier to debug. On the other hand, another good thing is that an interpreter is essentially an operational semantics. You can use it as a definition of language. And many people have done this. If you use it as a definition, then you don't have to prove it's correct because it's correct by definition. Well, the second Polynomial projection, is that you can produce a compiler by specializing the specializer and with respect to the input. And this is very much like compiling a compiler that's written in its own language. The only extra twist is that we have the partially known input, namely the interpreter. This compiler is constructed by self-application, using the specializer to specialize itself. Now, this looks like maybe an interesting exercise in algebra, but believe it or not, it actually works. To show that it works, you have to have programmed the specializer, and you have to run it on itself. The output, I can say from personal experience, is the output is a compiler that looks and feels like a compiler. It has a dispatch on syntax. It's going through looking at each of the commands, each of the statements in the source program, and it's generating code for them one at a time. We've done a number of papers and demonstrations. There's a completely self-contained specializer in our partial evaluation book, for example. Now, by the same kind of reasoning, and I don't think I'll go through this in detail, but it's exactly the parallel reasoning to what we did for the correctness of the target program. We can show that the compiler that we produce in this sense is in fact a correct one. And what it means to be correct is a compiler, if run on a source program, produces the target program that we talked about earlier. Now, this is getting to be a little hard to understand when you're online debugging the code, trying to make sure that the specializer actually works. It does work. It took us a year to get it right the first time, a year of hard work, but eventually we did. One of the big breakthroughs was something that we called binding time analysis, which has to do with identifying parts of the program that can be executed early, that depend only on the static data, and the parts of the program that have to be executed at runtime. Because the early parts you can compile away. The parts that cannot be executed, you have to generate code for. So actually, the correct compiler is got by specializing a specializer with annotations that has information which parts can be done early and which parts must be done late. The reasoning is the same kind of algebraic manipulation that I showed before, and is in this respect. Finally, the third Polynomial projection was that the result of specializing the specializer to itself is a compiler generator. And again, it's bootstrapping. If we know what the compiler is this result, then by definition of specialization, cogen applied to an interpreter will produce this compiler. Let's see, where was it? Yes. This is still harder to understand. And I will admit, like I said, that the compiling by self-application was difficult. It took us a year to get right. After about 9 or 10 months, we got the first version to work. It took a 3-line program as input, and it produced a 500-page output. That 500-page output ran correctly. Our computer was big enough that it could give the answer, but it was at that point that we realized more information was needed. And that was where this binding time annotation came into the picture, because the compiler that we were generating was spending a lot of time trying to figure out, can I do this And if I can do this, then do this. And if I cannot do this, then generate code. It was much easier if we marked the program and just gave it information saying, yes, you can do this, or no, you cannot do this. And that was the effect of this. At first, it was by hand annotations, and then eventually we figured out how to do it by computer. So the net result was that it worked. Once we got that to working, then it was just a matter of time before and hacking before we got the third projection also to work. Now, where is all this going? Well, basically, what I'm telling is a story of that it was fascinating to look at programs that are run on themselves. And the surprising thing is that this can give useful results in practice. It's not just a paradox. It's not just the kind of thing that philosophers like to think about, but it actually can produce good code. It wasn't the first example of self-application. Namely, Kleene in 1938 proved what he called a second recursion theorem. And I'm not going to go into details of the technical details, but basically it's saying that for any program, that you can find another program which, when given its input, will achieve the same effect as running the original program on itself and that input. And forgetting about...
So,
yes?
is it missing the star?
Oh, okay. All right. Good question. The point is that given a program that expects two inputs, then what Kleine's construction does is it produces a new program which would achieve the effect of running P with the new program as its first input. So you're quite right. It's not exactly running it on itself, but the point is that program P has a program input and a data input, and it's saying that you can choose the program input such that if you ran that program input, you would get the same effect as P run on both. And the proof in Kleine's paper is something like 8 lines. It's very short. I've adapted it here to my notation, but it's Kleine's proof. And it's saying that given program P, you can find something by first writing a program that given an input will specialize that input to itself. And this gives a new program, and then that new program is specialized to itself. And at this point, the intuition is totally lost. But you can follow the equations that define how specializers work. And yes, the algebra works. And furthermore, you can program it, and we have done so. And yes, the programs do what they're supposed to do. So there is something interesting going on here. And again, it's a constructive use of self-application. Now, I maybe should have begun this discussion by saying everybody knows self-application is a bad thing, because it is the way that you prove the unsolvability of the halting problem. It's self-application is how Turing showed that there is no program that can decide whether a program terminates. And that was by self-application. And that's a negative use. But these are positive uses of self-application. This is what I found was interesting. Now, at this point, I'll shift gears a little bit and just mention the historical developments. The Turing and Kleene did their fascinating work back in the 1930s, back when cars looked very strange. And Futamura came up with the projections in '71. It was a great idea. he tried to implement it, and it didn't work. His target programs had bits and pieces of the interpreter, so that it wasn't really very fully compiled. Valentin Turchin's work on supercompilation began around the same time. Well, Turchin independently discovered the Futomura projections, and he was also generalizing compilers. I first heard about it from Andrei Yershov, and this was 1981 roughly. He was giving a series of talks called The Essence of Compilation, and or he referred to it as mixed computation, where you're mixing the computation of the program's static input and the program's dynamic input. And he came up with a great phrase, the generating extension, which is something that generates programs. Around 1980, I first met Turchin, and he gave a fascinating and interesting talk that was unfortunately incomprehensible. It sort of made sense, and it had to do with compiler generation, but it was very much tied to his special language, the Rafale. It was hard to see the general patterns. Then I heard Yershov give a lecture on the what's called the Futomura projections, and once I understood that it was not a type error to run a program on itself, then it began realizing that there was an interesting problem. And we started work on it at Copenhagen and finished it after about a year of work. In '87, we had a workshop in Denmark on partial evaluation and mixed computation. About half of the participants were Russians. People, Sergei Romanienko, Andrei Klimov, Andrei Yershov, and many others. Since then, there's been, yes, I think Bulyonkov is there as well. Since then, there's been a lot of interaction, and other people in the world have gotten interested in program generation, especially by applying what is traditionally called the Futomura projections, although it seems to have been invented by several different people at several different times. So there's been a common interest here. Finally, the last few slides I'll mention are yet another use of self-application, of running programs on themselves. And this is in the area of complexity theory. And a change of focus. For now, I'm going to look less at problems and look less at programs and more at problems. And a decision problem, if you're given a set of values A, then the decision problem is given X to decide is X in A or is it outside of A. So you want to give a yes or no answer. Like if the input is the number 1337, the output could be yes, it is a prime number, or no, it is not a prime number. So the decision problem is to decide which side of the set of primes we belong. So a decision problem is to give a correct answer. And something that you probably, I'm sure you've all heard about in your beginning programming computer science courses is P or P time. It's the set of problems that can be solved by some program that runs in polynomial time. What it means to run on polynomial time is that for any input that the program gives an answer, a yes or no, within time that is bounded by a polynomial in the size of the input, in the input. And so basically what we require is a program P and a constant K such that P does decide the question, the membership question, and it runs in time at most n to the K, where n, the input size is n, and it's considered variable. The program, the input can be bigger and bigger and bigger, and you ask what happens to the asymptotic runtime. So for example, if you ask, there are many examples. Whether a number is prime or not, for example, if a is a set of primes, this can be decided in a polynomial in the number of bits in the input. Okay, now there are a bunch of complexity classes. P time is the one I've just talked about. Log space is a smaller class, which is it contains the programs that are decidable by programs that run with no storage. Programs that run with only pointers to the input. And here's a nice simple example of a log space problem. The problem is to decide, is the input a palindrome? Does it read the same from front to back as it does from back to front? And you can decide if a string is a palindrome by a simple algorithm that has a pointer to the first symbol, a pointer to the last symbol. It says, are these equal? If they are, then it moves the first pointer right one and the second pointer left one. And then it checks, are they equal? And you repeat this until you come to the end. Actually, halfway would be enough, but in any case, it is something that you can obviously do using only pointers. You don't have to have storage. And this defines the class of log space, which is an interesting class because surprisingly many problems are computed in solvable in log space. P time, everybody knows, is important. P space is the set of programs that can be solved in a polynomial amount of memory. Now this doesn't bound the runtime, so they can run in exponential time. They just have to have limited memory, and so forth. You can define larger classes by increased bounds on the resources, increased bounds on what you consider a reasonable amount of time or space to solve a problem. And this gives a hierarchy. Now, why is this hierarchy interesting? Well, partly because each of these classes corresponds to a certain restriction on programming style. Log space is a more limited programming style than P time, because P time you have the extra memory. You can write down bits of information. P space gives you more time, etc. Is every log space, is every P time problem solvable in log space? I don't know. Nobody has known this. It's been an open question for a long time. Is P time contained in P space, properly contained? Nobody knows. About the only thing we know is that if we increase the space bound by a lot, if you go from log space to polynomial space, or if you increase the time bound by going from polynomial time to exponential time, then you can solve some new problems. So there are a few proper containments in this complexity, but the interesting ones are still open. How do we show even these ones that seem so extreme as to be unsurprising? Well, that is proven by self-application, the so-called diagonalization arguments. What you do is you invent a problem which can simulate any log space program and then do the opposite. Well, this simulator cannot be simulated in log space, because if it did, it would give the answer true if and only if it gives the answer false. It requires a self-interpreter. The people who first proved this weren't thinking of interpreters, but that's how the proofs work. If they construct a problem which has a program, and the way this program works is to simulate its input program applied to itself to within a polynomial, a log space bound, and then reverse the answer. That is a clear-cut example of self-application. It's rather like the Futamura projection, the second Futamura projection, but it's proving a negative result. It's proving there are problems that can be solved in P-space. It cannot be solved in log space. And, well, at this point, we say, gee, wasn't Futamura a genius? But in fact, the problem goes back to 1891. It's the same kind of reasoning that Cantor used to prove that a set of real numbers is not countably infinite. And the proof he had was say, well, let's assume that you can enumerate all possible real numbers. Then I can construct another number that is not in the enumeration by changing elements at the diagonal. And Cantor wasn't thinking in terms of algorithms, but his proof can be thought of. It's essentially the same kind of thinking that's being used for this diagonalization result. So this is a rather fascinating thing, that this self-application keeps popping up again and again in new contexts. Okay, and finally, the last couple of things, and these are relevant to, for example, Ilya Klitschnikov's work on supercompilation, is relations between complexity classes in programs. Essentially, this was a theorem that grew out of some of my work in complexity theory, and it was a characterization of p-time by means of programs and log space by means of other programs. And what's the difference? Well, in the first place, these two equalities involve two transformations. You show for any p-time problem, you could find a cons-free program that solves that same problem, and vice versa. You show for each cons-free program, you can find it can be simulated in polynomial time. Now, why is this relevant to supercompilation? Well, the difference between these program classes is that the log space programs are flat. They are tail recursive. The cons-free programs are not necessarily flat. They can have nested function calls. So the difference, well, supercompilation, as any of you have had experience with trying it out or looking at the examples carefully, we can see that what supercompilation very often does is it flattens programs. It takes a program with nested calls and produces a program with no nested calls. A standard example is, say, append of x's, y's, z's. That has nested calls, append of append. But supercompilation can transform this into a program that scans the x's input and produces a result, and then scans the y's input and finally produces the final result. That is replacing a program which has nested calls, append of append, by a program with no nested calls. And suddenly this begins to be interesting, because this replacing nested calls by unnested calls is the same question as the question whether p-time properly contains log space. So the point is, if supercompilation can eliminate all nested calls, if it can flatten every program, then p-time equals log space. And something like 30 years of research would be over. People have been looking at this problem for a long, long time. On the other hand, supercompilation can eliminate a lot of nested function calls. And understanding how much it can and how much it cannot is suddenly interesting because it relates to another open problem. And there's an old smart remark saying, if you cannot solve your problems, at least try to classify them. And that's what people do in complexity theory. We don't know whether log space equals p time, but at least we're understanding the question better by being able to, and relating it to other questions. And this is related to this question of complete problems. Namely, a complete problem is one that is hardest for its complexity class. Let's see, yes. Yeah, well, for example, this hierarchy of problem classes here, a complete problem for p time is a hardest problem for p time. And what hardest means is a technical thing, that if the complete problem is solvable in log space, then every problem in p time is solvable in log space. So let's see, where was I? Yes. Well, it turns out there are problems complete for each of these classes. CV is the circuit value problem, and it's a very simple-minded interpreter problem. It's saying if you're given a straight line Boolean program, you ask, does it give true as a final result? And so, for example, if you have this program, then you can just simulate it and discover that, yes, it does compute true as the final value of x. And it looks like a pretty trivial problem. But not together with, but independently, Ladner and I have shown that if the circuit value problem is solvable in log space, then p time equals log space. So this is a very significant relation, let's say. It doesn't answer the question, but at least it gives helps us to classify. And now suppose we talked about that hierarchy with log space, p time, p space. These were all deterministic programs, programs like you would write in C. Now, if you allow non-determinism, you allow programs that can guess, that can, for example, say, is this formula satisfiable or not, or guess a path through a graph, then it seems that you get more power. What are these containments? They are also unknown. There are many open questions in complexity. There's not many answers, but at least we're understanding the problems better. And a long-standing open question is p time equal to np time? It's the question, is p equal to np? It's one of the standard things in an early computer science course is to describe the problem. And it's worth solving, because if you can solve it, you'll get $1 million. The Clay Mathematical Research Institute in the States has a standing offer, and if you can, it would be a good PhD thesis if you did that. In any case, where I'm going is that this is in the direction, it's something that you have run across before, and it's an example of a complete problem. And finally, I think what Steve Cook proved back in '72 was that if a satisfiability problem can be solved in p time, then every problem that can be solved with guessing can be solved without guessing deterministically. So he started a very large area. And this problem that I've just described, or the circuit value problem, is a similar question, except it's referring to log space and p time rather than p time and input time. So I think that's the end of this very fast review, but it's basically a summing up that saying that a crazy idea of running a program on itself has turned out to have a number of applications. Some negative, like proving the unsolvability of the halting problem, and some positive, like the ones that I've been describing today, the Futamura projections and so forth. What at first seemed to be an academic exercise turns out to have consequences. And I think that's really the end of what I have to say on this. So, yes. Yes.
You mentioned that the Copenhagen group achieved Futamura projections in practice. Was the hardest piece to develop the specializer program?
The specializer itself wasn't so hard. It's a matter of keeping essentially to an environment, keeping the values of the static data, and keeping an environment that binds the dynamic variables to bits of code that will be generated in the output program. I don't know, does this answer your question?
Yes, the next question is what was the hardest piece of work for implementing Futamura projections?
Right, yeah, that's a very good question. And we had a pretty good intuitive idea at the beginning of how specialization could be done. What we did not know was what would happen when you applied the specializer to itself. The first problem was getting that to terminate. And there were three of us, and what happened was that one of us would work hard, would finally give up, and then turn the problem over to the others, and somebody else would work. It went so far as we wrote a sequence of programs called to pay 1, to pay 2, and so on. And what does to pay mean? It means tomorrow's outdated and useless partial evaluator. And at each stage, we would produce a new version, try running it on itself, discover it didn't terminate, try to figure out why, and then make a new version. Eventually, we finally realized that some to-pay number k, I can't remember what k was, it was about 20, finally, with the aid of binding time analysis, was able to be made to terminate. So that was the hardest question. That was the hardest problem of this.
But what is BTA?
Binding time analysis.
I see.
And the point is that the specializer is given a program and just part of its input. The effect was the staging of the computation. So, and the point is the binding times, we say that the static input has binding time 1. So if the input, if we have a program and its static input, then all of this can be done at stage 1. And then the last run, running the generated program, is done at stage 2. So these are binding times. Some variables can be computed at stage 1, and other variables have to be computed at a later time. And that's why we call it binding time analysis. It's finding out which variables can be computed early and which ones have to be computed at runtime. So basically, the hardest problem was getting the self-application to terminate. And the solution was realizing that binding time analysis gave a solution.
Thank you.
Yes.
Are there any successful examples of usage of Polynomial projections in industry use? So nowadays,
Okay, that's a good question. And at the time it first came out, we were very, very excited because, and we went so far as to write a partial evaluator for a subset of C. The problem was at that time, in the mid-'80s, hardware was still obeying Moore's law. So if you wanted your program to run twice as fast, you just had to wait 1 year, and the hardware would run twice as fast. So people weren't motivated to the kind of thinking that you had to do a good partial evaluator. Nowadays, things have changed. We're somewhere near the limits of hardware. And there are, I know of at least 2 industrial research groups in Germany that have been seriously taking another look at partial evaluation and thinking, can they use this for the programs they have? So there are people who are investigating it. It's not still practically used in a large scale, but people are, the question is beginning to be worth answering. So the answer, yes, it looks more optimistic now than it did earlier, but I don't have the final answer. Yeah.
Does it mean that splitting an existing program into several layers, each one interpreting the next one, might give a performance boost?
Yes, exactly. But to realize this performance boost, you may have to write your program in a different way than you would write it if you weren't thinking about this. And that's why it was, and still is, a bit tricky to use a partial evaluator. But it usually can be done. We had some good, for example, a ray tracer written in C that was tracing, making a picture of a scene. If you specialize that with respect to the scene, then you can get a program that will make the picture much faster. Yeah. There was a question in the corner. Yes.
You mentioned that conscript programs captures polynomial time.
Yeah.
What does conscript programs?
Oh yeah. Absolutely. I should have said that. It's almost any question you ask about programming languages tends to be undecidable. To give any statements about complexity, you have to restrict yourself to a decidable class. And if you imagine a scheme program that does not use cons, then the scheme program, it could still run in exponential time, but all of its variables are always pointers to the input. That's what I meant by cons-free. It's a sort of it's the kind of language that is difficult because you feel you're programming with your hand tied behind your back. But on the other hand, at least it's simple enough that you can come up with some definite results. And that's the way theory often is. Maybe you can't solve the real problem, but you can solve a simplification of the problem. And with luck, then eventually you can solve the hard problem. Yes?
I have another basic question. Could you elaborate on why log space means no storage needed? So why the name log space?
Oh, right. Good question. Basically, what we're talking about is decision problems. If you're given, say, a string of bits, then you want to answer, does this string of bits represent, say, a prime number or not? A pointer algorithm would have a program that has some number of variables that refer to different parts of the input. Now, you can ask yourself, if I did represent this in terms of storage, how many bits would I need? How much space would I need? Well, how many bits does it take to represent the number n? The answer is log n. So if you have a program that has some fixed number, x, y, z, then you could represent it with 3 log n bits in memory. So that's in a way that's it's saying it's not really memory free, but the number of bits you have is very small. You can't just rewrite all of the bits. So yeah, that's quite a reasonable question. Historically, it developed as a space-bounded Turing machine, where you had some amount of memory. And if that memory, in this case, would have been at most log n, k log n bits. Yeah. That's a very reasonable question, and the short answer was it made sense at the time, but now people don't use those definitions anymore, so it requires explanation. So it was a good question. Yeah.
So nowadays it could be called like const space.
Const free.
No, I mean constant space.
Oh, constant space. Yeah. If you take this assumption that practical programmers do, that a pointer can be put into one memory cell, only takes a constant amount of time. But that quickly gives you complexity theoretic problems. There is a difference between constant and logs. But we're so used to building our hardware that anyway. Yes.
So, returning to tomorrow projections, to obtain a compiler information code, you have to have interpreter written in machine codes and specializer written in assembler code. So, is it true that for practical application we have to write all specializer in assembler code?
Okay, that's also a sensible question, because normally when you think of compilers, you think of compiling from maybe C to assembler code. And it makes sense to compile from a language to itself. The kind of experiments we were doing were based on using scheme, in which programs are data objects. And very literally so. But if you add a change of level of the language, then you just add complication to the description without helping to answer the questions that are being done. And let's see. Yeah, okay. I think a question behind what you're asking was, is it necessary to write the specializer in one language and the interpreter in another language? And the answer is no. It works if you do them all in scheme or Prolog or some language that manipulates trees in a flexible way. So you do not have to go to a machine language level.
Yeah, but are there compilers that were created by specializing the interpreter, which actually act like normal compilers? They take source code and produce machine code. Are there such?
Oh, right. Yeah, one of my students did some of this as a master's project. Basically, he took the specializer and added a post processor that transformed the output code into machine code. And he showed that this did fit nicely with the other part.
The point was that it was rather trivial, that last part.
Yeah, it was as trivial as compiling normally is.
No, I mean,
Yeah.
I think it was was supposed to be much simpler, so the hard problem would be solved by specializing the interpreter, and then simply producing the machine code maybe was supposed to be simpler, or because if not, then what was the point of coming up with a compiler produced by the specializing interpreter?
Okay, yeah. The point is that this approach of using an interpreter to define a language allows you a great genericity. You can write very general programs that can accept many different languages as inputs. Whereas if you are restricting yourself to one source language and one target language, then if you want to expand your source language, then it's painful. If you want to expand C by adding a few features, then that's a major change to the compiler. But if the compiler was represented as an interpreter and a specializer did it, then you could expand the interpreter in a readable source language. So flexibility, I think, is one of the main points here.
Are there any questions? No? Let's take a chance. Well, that's it.
Okay. Okay. Good. No, thank you.
Thank you.
Is that? Yes.